In the second part of this lecture, we're going to look at two different models of computation and show how they closely relate to the logic FPC that we've been looking at. We've alluded to these, both these models in the first lecture, and we'll look at them in a little bit more detail. So the first of these is that of relational machines, which I illustrated with this picture, which is meant to look like a finite state control, like with a Turing machine. But now it has access to a collection of relations rather than strings written on a tape. So, roughly speaking, the idea is the input is a relational database, which is for us just a finite relational structure. We have a memory store which consists of both relational and numerical registers, right? So registers in which you can store variable relations and numbers. And operations, the basic operations of relational algebra, like join, projection, complementation, and some mechanism for counting. And I stated that properties expressible in FPC are exactly those decidable by such a machine in polynomial time. Now I'll give you a somewhat more formal definition of this machine. You fix a relational vocabulary, R1 through Rm. So the input to our machine is going to be a sigma structure. The relational machine has fixed relational registers R1 through Rm, on which the input will be given. So they're initialized to some sigma structure. There is a fixed number of variable relational registers, P1 through Ps. So each of these can hold a relation of fixed arity. And so note in particular that the number of such registers and their arity is fixed beforehand by the machine and is independent of the input. And we have a collection of numerical registers, C1 through Ct, each one of which is capable of holding a number. So if you're familiar with register machines as a universal model of computation, these are really registers machines with additionally a relational store. The program of such a machine will consist of certain atomic actions put together with the control constructs. The atomic actions are the following. You can assign to a variable register one of the inputs, so you can just copy the input into a variable register. You can take the union of two relations and put it into Pi. The arities have to match, so Pi, Pj, and Pk have to be all of the same arity for this to work. You can take a projection. So what does this mean? So Pj here has some arity greater than k, and A1 through AK are indices between 1 and k, between 1 and the arity of Pj. And Pi is simply the projection of the relation Pj on that set of indices. So for instance, the projection on 1 of some binary relation Pj will be the unary relation consisting of the first coordinate of Pj, and pi2 would be the projection on the second coordinate. This is the relational join of Pj and Pk, again on some collection of coordinates. So you take those tuples in Pj and those tuples in Pk which agree on the coordinates A1 through Ak, and you take the collection of all such tuples you can form. That's the relation Pi. And I'll allow complementation. So in Pi you can take the complement of a relation Pj. Note, for complementation to make sense, in the relational algebra we had set difference. For complementation to make sense, you really need to assume you have fixed the universe of the structure beforehand. So we're assuming here that the input to the machine is a fixed relational structure and therefore has a fixed universe. So it makes sense to take the complement of a relation. On the numerical registers, I'll allow an increment operation, and I will allow you to count the number of tuples occurring in any relation Pj and copy it into a numerical register. The control constructs are really a branching and a looping construct. For the Boolean conditions, I'll just allow a test for 0. And now P here refers to any program. So you can recursively define a collection of programs. What I've defined here, of course, is Turing complete, right? Just on the registers, you have a register machine. But it turns out that the polynomial time restriction of these machines, and if you think of it as deciding a class of structures. Okay, so the input comes in the relations, and so you can't do an arbitrary computation on the numbers because you can't translate the relations into numbers except through this counting construct. Okay, so what you can do in polynomial time on these relational machines, I haven't exactly said something about the output. I mean, you can output on a Boolean value by testing a relation, whether it's empty or, which equivalently, count the number of elements and test for 0. So the class of relational structures is accepted by polynomial time relational machine by defining a suitable notion of acceptance, if and only if it is definable in FPC. And I'll leave that, as I said, as an exercise, 2 directions. Given such a machine, you can translate into FPC. There the difficulty is in, you have to inductively define the contents of these relational and numerical registers. And the other direction is somewhat simpler. You can simulate any formula of FPC using such a machine. The other model I said I would relate to is circuits, and I did this already to some extent, or at least stated the connection in the first lecture. But I'll run through it in a little bit more detail, and then eventually get to actually telling you how this is proved. So a circuit, remember, is a directed acyclic graph where you have source nodes, that is nodes with no incoming edges, which are labeled by variables x1 through xn, which we'll think of as Boolean variables. Any other node, so not a source node, is a gate. And if it has k incoming edges, it's labeled by a Boolean function of k inputs from some fixed basis. For example, the basis of Boolean functions and, or, and not, the classic basis of Boolean functions. But note here, and, or are arbitrary fan-in, so they can take any fixed number of k of inputs. Some gates are designated as outputs, y1 through the ym, and typically these will have no outgoing edges. So we can think of such a circuit as computing a function on Boolean values. So you assign a value to each of the n variables x1 through xn on the inputs, a value 0 or 1. You can compute the values of all intermediate gates, and you get a value at each one of the m outputs, and that gives you a 0-1 string of length m as the result. Now, this leads to the study of circuit complexity, where we think of a language L of, in other words, a collection of 0-1 strings, as being given by a family of Boolean functions, one for each possible length n. Now, any Boolean function can be given by a circuit made up of and, or, and not gates. If we can bound the size of the circuit by a polynomial in n, the number of inputs, then we say that this language L is in the class P/poly. This is the non-uniform version of P. If, in addition, the function that takes you from n, let's say n given in unary, to make this reasonable, to the circuit Cn is computable in polynomial time, so in other words, polynomial time in the value of n, then in fact the language is in P. This is effectively an equivalent characterization of the complexity class P. Those languages which are given by polynomial time, by a polynomial time uniform collection of circuits. For these circuit complexity classes like P and P/poly, it makes no difference if we just use and, or not, or we throw in more possible Boolean functions into our basis, unbounded fan-in, threshold gates, counting gates, because any of these can be simulated by and, or not circuits using just polynomial size circuits. We can replace each of these gates by a little polynomial size gadget circuit that computes it using just and, or, and not. On the other hand, it's known that something like threshold gates makes a difference if you put some restriction on the circuits. For instance, if you consider bounded depth circuits, right? So AC0 is the collection of those languages were accepted by bounded depth. So here you limit the depth of the circuit to some constant, bounded depth polynomial size families of circuits with AND or NOT gates, but of course you allow unbounded Fanon on the gates, as we already did. TC0 is the same thing, but we allow AND, OR, and NOT gates as well as threshold gates, right? And it is known that TC0 is more powerful than AC0. So these give you different classes. So putting a restriction on the circuit family makes the basis count. So threshold gate, if you've not seen this before, is simply for each value of k and t less than k. This is a function which takes k inputs and gives you a value 1 if and only if at least t of the inputs are 1, right? So if the number of inputs which are 1 exceeds some threshold t. Right. Now we're interested in circuits which take not just some set of strings, but the input is some structured objects like a graph. So we want to decide not a language, but a class of, say, directed graphs. We can think of this as being given by a family of Boolean functions. For every n-vertex graph, you can turn it into a Boolean string of length n squared just by enumerating the adjacency graph of, the adjacency matrix of the graph. And we hence get a Boolean function. Right? A graph on the vertices 1 through n has n squared potential edges, and so we treat it as a string in 0, 1 to n squared. But because it's a class of graphs, and therefore closed under isomorphisms, reordering these vertices and then giving us a different adjacency matrix, and therefore a different string in here, should make no difference to the circuit. So the function computed by the circuit, each of these functions, is invariant under the natural action of the symmetric group on n squared, right? And we call such functions graph invariant. More generally, if you have a relational vocabulary tau, you get strings of length tau n, where tau n is simply the sum of n raised to the power of the arity of each of the relations. And you can write down a tau structure as a string of zeros and ones of this length, right? We kind of saw this before when we encoded structures as strings. There we had little separator markers to mark out each of the relations, but if we know the relational vocabulary beforehand and we've fixed the sequence of relations, then we can forget about the markers and treat it simply as a binary string. Once again, an n-element structure determines an action of this symmetric group Sn on such strings. And we say a function is tau invariant if it is invariant under this action. For simplicity, I will stick to talking about graph invariance, the special case where tau consists of just one binary relation. Now, we say that a circuit is symmetric if every permutation of 1 through n extended to the suitable permutation on tau n can then itself be extended to a permutation on the whole circuit, which is an automorphism. So it doesn't change the shape of the circuit. So you can permute, you can reorder your graph or your tau structure as you like, as long as it's the same structure, and give it to the circuit, and a simple reordering of the gates will give you back exactly the same thing. So it's clear that every symmetric circuit computes an invariant function, because that's just built into the definition by the structure. But the converse is false, right? In principle, you can have circuits which compute invariant functions, but are not actually symmetric. But symmetric circuits arise fairly naturally, and again, we saw this briefly before. If you take a formula, for instance, of first-order logic, it gives us a uniform family of circuits Cn, which are symmetric. So how do you do this? You basically take every subformula and any assignment of values to the free variables, right? Values from the universe of your input structure, or from 1 through n, if you will. And for each of those, you have a gate. So the idea is, for a particular input structure, the gate corresponding to psi a bar will evaluate to true if and only if, in that structure, the formula psi is true of the tuple a bar. Existential quantifiers translate to big disjunctions. So there exists x theta x a bar. Suppose this is psi a bar. We will have a theta a bar. I will write this again. Theta a bar 1, theta a bar 2, and so on up to theta a bar n. And we take a big disjunction of these. And this will be our gate psi a bar, right? If we carry out this translation, we observe that the circuit we get has constant depth. It's in fact given by the quantifier depth of the formula of first order logic we started with. And it has polynomial size. In fact, the size is bounded by c times n to the k, where n is the size of structures we're looking at. It's this. C is the constant bound on the number of subformulas of phi, so it's independent of the size of the structure. And k is the maximum number of free variables in any subformula phi, which is a useful fact, because the maximum number of free variables in any subformula is exactly the number of variables you need to write down the formula. Okay, so that's worth keeping in mind. And the circuit is symmetric by construction, because if you take any permutation of 1 through n, then for every gate, there is a gate which is its image under that permutation, and that is an automorphism of the circuit. What if we started with a formula of fixed point logic? Well, the point is that you can take a formula of fixed point logic, and we know that there is a k. It says that if we unfold the inductions, we get a formula of Lk, or as we noted before, fixed point, the formula phi is equivalent to an infinite family of formulas of Lk. But equivalently, for every n, there is a single formula of Lk. So there's a formula of first order logic now, using k variables, which is equivalent to phi on all graphs with at most n vertices, because you unfold the fixed points, but you only need to unfold them up to some bound, which is polynomial in n. This formula phi n translates to, it has quantifier depth, n raised to power c for some constant c. And it has at most k free variables in each subformula for some constant k. Well, it's precisely that number over k. It is roughly twice the number of variables that appear in phi itself. Okay. And now, by the translation of first order formulas we had, it follows that every graph property definable in FP is given by a family of polynomial sized symmetric circuits, because the translation of this into a circuit has, well, polynomial depth, and the size of the circuit we said was some constant times n raised to the power of the number of free variables appearing in any subformula, and this is now bounded by a constant. What happens if we start with fixed point with counting? So this should be FPC. For every sentence of FPC, there is a k such that for every n, we have a formula now not of Lk but of Ck. So now this formula again has polynomial depth and a constant number of free variables. You can translate to a circuit. The only difference is that in the translation now we have occasionally these counting quantifiers. There exists at least I elements x such that theta holds of x, and there may be other free variables y, right? So this is pi y. Now, when I had an existential quantifier, I said it's a big disjunction. A universal quantifier would be a big conjunction. This counting quantifier translates into a threshold gate. And that's really the only difference. So once you allow threshold gates, I can translate formulas of FPC into polynomial size circuits, which are symmetric. Instead of threshold gates, it suffices to take majority gates. There's a normal form. This is still FPC. There's a normal form which for these formulas phi n, where you can do away with counting quantifiers and use what are called Rescher quantifiers instead, and that gives you a basic with majority gates. But you can't do away with these altogether, with the majority or threshold gates. So it's possible to prove that any translation of threshold gates into and or not gates while keeping polynomial size must break symmetry. Okay, but we will stick to symmetric circuits with threshold gates. And the key result is this one, that there is a translation in the other direction. If you start with a polynomially uniform, polynomial size family of symmetric circuits, let's say in the Boolean basis, so just and or and not gates, then the class of graphs it accepts is definable by a fixed point formula. But now, it's not a fixed point formula interpreted on the graph. And there's an interesting reason for this, because I can give you a trivial family here, which decides whether the number of elements is even or not, right? It's the family of circuits which, when n is even, simply evaluates to true. When n is false, when n is odd, evaluates to false. And we know this can't be done in FP. So we have to give the logic somehow the power to at least say, at least know the size of the universe. And we do this by taking the graph and a disjoint union with a simple linear order of size n. Now, fixed point formula evaluated on this can do any kind of polynomial computation on the linear order. So it can determine any property of the size that can be decided in polynomial time. But it cannot relate that order to the graph in any way. And so it remains graph invariant. So in this logic, you can say that the number of vertices is even, but you cannot say, for example, that the number of edges is even. And that's now, we know this about FP by a simple pebble game argument, but that effectively gives us a circuit lower bound as well. In the case of fixed point with counting, the connection is much cleaner. We don't need the separate linear order because that's kind of built in with the counting. We have a domain of numbers on which we can do comparisons and arithmetic and so on. So we simply say that a class of graphs is accepted by a p-uniform polynomial size symmetric family of threshold circuits, if and only if it's definable in FPC. Okay, it's a nice, and this shows we have a characterization of FPC purely in terms of circuits. This is standard circuits with threshold gates, which are known. What we have done is effectively add the symmetry condition. So in a sense, FPC is a very natural fragment of polynomial time characterized by the fact that the computations are symmetric. So we think of this as symmetric polynomial time. This result has some nice consequences. For instance, we get essentially a natural, purely circuit-based characterization of FPC, as I've said. Also, inexpressibility results for FP and FPC yield lower bound results. I already mentioned, we can say there's no polynomial size family of symmetric Boolean circuits deciding if an n-vertex graph has an even number of edges. Adding threshold gates gives us more because we know FPC can express that the number of edges is even. But also we know that there are polynomial time properties that are not in FPC, and therefore there are invariant circuits of polynomial size which cannot be translated to symmetric circuits of polynomial size, even with threshold gates. Or rather, any such translation will involve more than a polynomial blowup. These are all consequences. But another way of thinking about it is our methods of proving inexpressibility in FPC using bijection games can also be seen as a method for proving circuit lower bounds. And we'll pause here now for and then look more closely at the lower bound.